Welcome to the Water Research Foundation webcast on Project 5087 on Biological Nutrient Removal Instrumentation and Control Selection Adventure. So my name is Jian Zhan. I'm a research principal with the foundation, and I will be moderating today's webcast. First, let's go through several housekeeping items. Please submit your questions through the question box at any time during the presentation. We will do a Q&A at the end of the webcast. Slides and a recording of the webcast will be available for download from our website. And at the bottom left of your screen, there's event resources, so on which you can download the slides now. And there's also a link to the project page on our website. We will be certificate of completion will be automatically generated at the end of the webcast. If you have any questions, please contact Michelle. Her contact information is here listed on the slides. And also, lastly, it's important for us to hear from you regarding today's webcast. So please stay until the end to fill out a quick survey. So this project was completed by a strong team led by Sue Gaswa. She's with Woodward and Curran, and she's the principal investigator PI of this project, supported by 5 other co-PIs. We have Paul Dombrowski and Maureen Neville from the same company. We have Dr. Tucker from the University of Massachusetts Amherst, Dr. Muir from Northeastern University, and Dr. Snowland from Hatch. Now, let me hand it over to Sue.
Okay, great. Thank you. All right. Well, our core team is a collaboration between consultants, academia, and a software group. But this project is really about synthesizing the state of the art, and our project partners were essential to the success. They provided feedback, a lot of information via utility surveys and case studies. So I just want to thank all of the organizations and individuals listed here on this slide, as well as your teams for supporting the project. Also want to thank the PAC members. Our workshops throughout the project were really impactful, and we appreciate your input that you provided to us and helped us shape the results. And finally, want to thank our WRF program manager, Jan, as well as before him, Stephanie Fevig, and the whole WRF team for the opportunity to develop this work and supporting us throughout and sharing it with you today. Okay, so we've got a big lineup. We're going to go through 10 agenda items, but we're going to do it in less than 90 minutes. We're going to land this plane on time. We're going to start off with an overview and background, and then work through introducing the 2 main deliverables that were part of this project. And you'll get a chance to play along on the app that we built, and you'll also get to see a live demo of the simulator with the training questions that we customized for this project. And then finally, we'll spend some time with you in Q&A. So without further ado, I would like to pass it over to Amy to kick us off.
All right, thank you, Sue. So I have the great honor to give you all the introduction of where we started in our thinking on this project and how we came to propose this. So we actually came to the table thinking not so much about all of the plants that already have implemented nutrient removal and other biological processes, but thinking about all of the plants that haven't yet done that. And what is the process by which we go from existing infrastructure to what we might want to have as future infrastructure? And we systematically tried to lay out everything you would need to think about from the beginning of that process to the end. We actually started even earlier than that with a discussion, roundtable discussions, actually a series of these with smaller and larger plants in the New England area just asking folks, what's on your mind? What do you need? What do you know? What do you not know? What have you tried? What works? What didn't work? And we came away from this with a true appreciation of the diversity of different approaches that are out there, and especially with the differences in technological integration into these different plants. So everything is completely automated and being run through the cloud to, well, we had one pH sensor once, but it got frustrating, so now we don't. And we thought this is a lot of different people at a lot of different starting lines, and how do we get information out to this community in a way that would really be helpful? How can we think about the most appropriate way to move different plants forward? So we did a systematic approach from our side to figure out what is the information that would be helpful, and then how can we organize it into a way that will be the most useful, fast track for everybody else to access that information. So we started with a literature review. We kind of went to published papers, to old WebTech abstracts, everywhere we could think of, to see what's out there. And I don't think any of us will be surprised that a lot of information that we were looking for is not in those sources. A lot of this is just in the minds of folks who are actually operating plants. So with the gaps in mind, we then went out to everybody in the field and said, hey, can you tell us what you're up to? Can you tell us what you're experiencing? What have you tried? What worked? What didn't work? In these surveys, we really strove to speak to plants of many different sizes with many different strategies to get as much diversity as possible to represent what's actually happening in the field. We then narrowed in from those surveys on a few key questions that seem to be coming up of, are these particular sensors useful? How could we move forward as a field? And did some very concentrated testing that Nick will talk to you about. Our deliverables from this were really from the beginning not for it to be a report. So I've said a few times, we wanted this to be information that was accessible in the easiest way possible, and hopefully in a way that's enjoyable and not a burden to work through. So we came up with sharing in this format, but also having this app that Sue mentioned and a whole host of different tools that we've put together that are linked from the website, as you already heard. So this is really not just one report that you can download. It's a host of different resources that we'll walk you through today, and you can start in any of those different places, depending on where you are in your specific journey. Those deliverables that we would like to kind of give you an introduction today start with thinking about the audience as lots of different folks in this sphere. So anyone from operators and actually like out of the front lines to somebody who's really thinking about the big picture of the evolution of the plants over time. And then getting us all the way to the point that we can simulate what we think we want to do and practice that before anything is actually built. So can we go from envisioning what might be interesting, costing that out, and then actually testing it in software to see if it makes sense, all ahead of really trying to make an investment in infrastructure upgrade. And that last biggest gear, that's most of what we're going to be talking to you about today, is all of these different tools so that you have a sense of what's available, and hopefully you can spend some time on your own digging through there and seeing what can actually, what knowledge you can pull out. And with that, for that first tool, I'm going to hand it back to Sue.
Great, thanks. Okay, everyone, are you all ready for an adventure? I'm going to spend the next few minutes showing you the framework that we built that houses all of the tools, and it includes a fun little journey that you get to go on. So if you've got a phone with you, you can scan this QR code. It will take you right to this website that's listed down here at the bottom, WRF-BNR-selection-app.woodardandcurran.com. And that will get you to the page, the starting point of this adventure. And we just really wanted to have some fun with this. Like we said, make it as engaging as possible. So we couched it as an adventure and a canoe trip down the river. So I'll just give folks, a couple more seconds to type in. And if you don't get to it, we'll have links to it at the end. You'll be able to follow up and take a look at it. And you can also access this through the WRF website. It's fantastic that WRF is allowing us. This is a public plus project, so you don't have to be a WRF subscriber to be able to get access to this information. Okay, so for those of you that have opened up, you can play along. Otherwise, I'll kind of lead us all through the adventure. So this is the starting page, and this introduces the app and lists all the tools that are embedded with it. But, it really gets started with your own individualized adventure. You get to choose your route. And the more questions you answer, the more customized the suggestions are for you. But, in this day and age of TikTok, we didn't want to make it too long. So it's a pretty quick adventure to go on with us. So click Start Your Adventure to play along with us. All right. And that leads you to the first question. And the first question is, what is your reason for being here today? Are you here because you're interested in nitrogen removal or phosphorus? Maybe you're interested in removing both nitrogen and phosphorus, or maybe you're just exploring. So you can click your choice. We're going to click both nitrogen and phosphorus and see where that adventure takes us. And then you'll move on to the next adventure, keep paddling, and you land to question 2. And question 2 is, what systems do you want to control? Choose all that apply. So you can choose more than one: aeration, chemical, pumping. Let's choose aeration. Hey, and let's throw in chemical too. Okay, and we'll shoot the rapids to our last question here. And that is, what best describes your vision for a BNR control system? Choose one. One, I want minimal instrumentation to maintain. Or at the other end, I want lots of control and the ability to optimize performance, minimize chemical and energy costs. I'm okay with additional capital and O&M costs associated with instruments. Or maybe the middle ground, somewhere in between. Let's select that and land the canoe at our scenic lookout point. And at this scenic lookout point, what you'll get is a customized list of control systems that may be applicable to what your preferences are. So you don't have to start with the universe of all of the control systems. You can start by previewing what the ones that may be most applicable to your interests are. And it just provides you with a short overview of what the control system is, as well as its applicability. But all of that information and more is included in the last page, which is the final destination. And these are all of the tools that are available so you can go deeper in your exploration of BNR controls and instrumentation. So with that, I hope you had a fun chance to run through the adventure once. You can keep going back, doing it as many times as you like, but I'm going to pass it to Maureen, where she's going to walk through some of the tools that are embedded in the app.
Thank you, Sue. As Sue mentioned, I'm just going to go a little bit more in depth on these first 4 tools: the utility survey, controls matrix, the instrumentation matrices, and the case studies. So going back to that final destination page, we're going to start looking at the utility survey results. As Amy mentioned early on, when we did the literature review, we felt like it was very hard to track down certain information we were looking for. So, especially maintenance information on instruments. And we also felt it was hard to be able to get the quantitative information we might want. So, how much does it actually cost to maintain those instruments? So we set about doing a utility survey. We sent it out to 1,000 facilities across the US, a few in Canada. And we wanted to get some general background on the facilities, where are they located? What are the permit limits, the capacity? We confirmed the control systems they're utilizing, what sensors and analyzers they use in concert with those control systems, what O&M are they doing on the instruments, and then tried to delve a little bit into what benefits they're gaining from implementing the control systems, what challenges they've faced. So when we got 72 responses back, and the information we received, we did visualize in Power BI, and so we're showing a little bit, a couple of those graphs here to give you a sense of the distribution of capacity of the facilities that responded, and also the location of those facilities. So we did get a good distribution. We do have some small facilities. So I think you can see the hot pink, 7 of those. And then all the way through very, very large facilities. So that was good for us because we were able to capture the people that are probably ahead of the game in terms of implementing control schemes. But then we also have results from facilities on the smaller end that maybe just haven't had as much experience or are just getting into it. And from the distribution from the map, you can see there are a number of facilities in the New England area where there have been nutrient limits for a number of years. We do have some representation in the Midwest and in California as well. So the first tree map I'm showing here is results of which control systems are actually being utilized by the respondents. So the most prevalent was DO control, a decent number implementing RAS-WAS pumping control, SRT control, IMLR. We did include metal salt addition as part of the survey, even it was for BNR control systems, but often people are adding metal salt in concert with EBPR, so we did include that control system as well. And the other takeaway from this slide is just that some of the more advanced control systems were more limited. So you see AVN 1, ABAC, we had 7 respondents. And we've done this presentation a few times with live audiences as well, and we feel like we get pretty similar distributions when we talk to those audiences. So this tree map was just to show what analyzers or sensors people are utilizing in concert with those control systems, with 65 people using DO control. Those 65 also have the DO sensors. The next most predominant was pH. This should actually be suspended solid sensor. That was the third most. That was a little bit of a surprise for us. Another takeaway from the tree map was just, if there is an alternative for a sensor or an analyzer, as you can see with nitrate, ammonium, that more people were implementing the sensor or had installed the sensor than the analyzer. So that was just, again, this is just to show the type of information we're getting back through the survey. And then we did individual dashboards for each instrument. We did dashboards for specific benefits, which control schemes are allowing you to perhaps save energy, which ones are helping you improve performance. Same thing for challenges, which control schemes maybe were expensive to implement. So we're capturing that in some of the dashboards. And then we have a dashboard like this for basically each one of the instruments. And the 4 circles kind of in the top left, all are trying to get at the O&M associated with it. So the first column is, quantitative. How frequently are you doing calibration or cleaning or preventative maintenance? And then the next 2 are more subjective. What's the ease of those actions? How acceptable are they? The level of effort associated with them. And we do have a little bit on O&M costs, but again, it's more of a qualitative. Are they acceptable, the costs? And so what the tool actually is from here is a compilation of all of these dashboards that you can link to and see the summary of all the results from all the surveys. And the main takeaway we had from the survey was, that DO control, DO sensors was the most commonly implemented. What came through the survey was the criticality of the maintenance being actually performed on the sensors, and most people felt that the BNR controls were worth it, but that there were some challenges associated with it. So we just went through the survey results. So now I'm going to touch on the actual control system summary matrix. as that Amy mentioned, we really wanted to provide things that would hopefully be reference points, individual reference points that would be very usable for people. So this is broken down by what you're trying to control. So aeration, pumping, chemical addition. So those same points that Sue went through in the app. And then basically includes a description of the control system, what outcomes people are usually trying to achieve when they implement it, different configurations you can have, the instrument related to that control system, and then additional considerations. And so I'm going to bring up a snip for what the DO portion of the matrix looks like. Might be a little small to see here, but in that first column, it tells you it's your DO control system. The next column over is a basic description of a DO control system, and this is actually the same description that you would see at your scenic lookout through the Adventure app. Then it talks about types of outcomes. So often people are looking to improve energy efficiency or really make sure they can hone in on the DO set point they want, either down the length of their bioreactor, or if they're implementing a low DO strategy. So you really need more precise control to dial in that DO. You have your configuration, feedback, but then often tied into additional controls. So whether it's a flow-based most open valve or floating pressure base. So that's also mentioned in additional considerations, that DO control is often implemented with even more sophisticated controls. And then again, mentions the instrumentation that you would utilize. It does mention here, airflow meters and pressure transmitters that are often included in aeration control schemes. Those aren't part of this study, but again, we're just noting what else you might need if you wanted to do DO control at your facility. Some other things that end up coming up in additional considerations include, are the proprietary systems associated with this type of control. So again, just to give you a kind of a flavor of what is included in that control system summary matrix. Next, I'm going to touch on the actual instrument summary matrices. So this summary here has the instruments broken down by whether they're sensors or analyzers. Then it shows how the method for the measurements, and then the analytes in that kind of final column there. And we actually have two summary matrices in the app. We have it broken down by sensor or analyzer as shown here, or we have it broken down by the analyte itself. So if you're trying to do ammonium, you can do either a sensor or an analyzer. DO, you're just going to have sensors available. So it's broken down two different ways on kind of in the summary matrices. And then if you actually dial in to an individual matrix, it's based on the analyte. So if you're looking at DO, it can tell you different manufacturers, model numbers, detection range, and accuracy, precision. Are there ancillary items that I require, like filters or cleaning systems? And it does also include, cost in 2023 dollars. And we know that, ultimately this is providing a snapshot in time for now, but it also does provide one location as a great starting point or jumping off point for someone who's looking to install these instruments. And this again, it's going to be small. So if you're on the app, you can pull these directly up and you can see what's included for all of them. But it has all of that information that I just listed through for each one of the individual analytes. So again, I'm just showing DO here, but it has it for all of them. And then the last tool I'm going to discuss are the case studies. And so, as I mentioned, we did get a lot of good information from the utility surveys, but we felt like we really wanted a little bit more. We wanted something more in depth. We wanted to be able to get real costs associated with maintenance of some of these instruments. So with these 11 case study partners, we asked for additional information, followed up with phone calls, and really got a lot of, I think, useful information for someone who's going to try to implement BNR control schemes. So these, as I mentioned, these are the 11 that we have. Some of them for all of these, we have, an aerial photo, we have your process flow diagram, very basic information about the facility, what BNR processes they have, what their permit limits are. And then we have tables that includes every instrument that they're implementing for BNR control, what maintenance they're doing on it, the cost of that maintenance, both in terms of labor hours, parts, and any outside third party servicing that they're doing. So we have that for all 11. And then for the 4 in orange, we actually have extended case studies. And so for those, there's just a little bit more information behind it. So there's a little bit more text, and it's going to talk, describe the control scheme a little bit in more detail, get into what benefits they're actually achieving by implementing it, how they're using it for process control. So there's 11 of the case studies, and when you click on it, it actually brings up like a summary page that shows you all the different locations, what processes, what BNR processes they have at their facility, what control systems they are implementing. So just to highlight here, with those 11 case studies, we do feel like we have a pretty good range of BNR processes represented, and a good range of the control systems that were included in the study. So the last slide I was going to go through is just to give an indication of what this looks like in terms of the case study themselves. So this is the one for Upper Blackstone Clean Water in Millbury, Massachusetts. And the case study for them and for all the extended is broken down by the control system itself. So again, it's going to give you a description of the control system. And then it's going to have this table where it's going to tell you how many instruments there are, where it's located, the manufacturer, the model, and then the year of installation. And then it's going to delve into the details of operation and maintenance. How much training have they done on it? How often do they validate? When we got to the case study versus the utility survey, we got a little bit more granular on on-site, minor adjustments that you're making for calibration versus actually sending it back to the manufacturer. So there's two lines when we're talking about calibration in these case studies. Then how often they're cleaning, what that cleaning entails, what preventative maintenance they're doing. And then the final table gets into the costs, so the quantitative here. So how much do they spend on parts per year? The cost for a third-party service contract would be there. They're not using it for DO, but they do utilize it for their orthophosphate analyzer. So that's in there for that section. How many staff hours do they spend a year on it? And then it's brought back to the annual O&M cost per sensor. And so this is what's in every one of those case studies, whether it's the extended or the not extended, the unextended one. And what I want to just highlight here is that when we were working with our case study partners, they were very willing and wanting to share the information, all the lessons that they've learned by implementing. And so the contact information for that facility is located in the case study. And so it's available for people to reach out and ask their own questions, even beyond what's presented. Okay, and with that, I'm going to turn it over to Nick. Thank you.
All right, thanks, Maureen. So the next part of our adventure here was talking about sensor cleaning and validation. So for this part of the study, we have moved on, and basically what we tried to do is give utilities a starting point as they build their own SOP. We looked at 3 different things along the way for this, including sample collection, sample analysis, and also looking at whether or not matrix adjustments were required. We did a whole bunch of field testing at UMass Amherst. There's the water resource recovery facility for the town is right next to our campus. So it was a really great place for us to be able to do that. We deployed some sensors and did some kind of routine maintenance and cleaning with them. And then we're also able to run some tests related to things like the importance of filtration on samples and some things like that. So on the figure on the right here, you can see the nitrate concentration in some samples that we collected, and we filtered a portion and we left another portion unfiltered. So the blue is filtered, the green is unfiltered, and then the diamond shapes that you see are ones that were cold, refrigerated at about 12 degrees C. We tried to depress the temperature a little bit more, but because we were kind of routinely taking the samples out and analyzing them, they were only able to get down to about 12 degrees, but we thought we still were able to get some good data from this. The other samples, the circles, are at 18 degrees C from a subset of those same samples. And the big takeaway from this is that unless you filter your samples right away, that concentration really starts to change. Even after a pretty short amount of time, it could be as short as like grabbing the sample at the aeration basin and bringing it back to your lab. You could have a pretty significant change in the concentration that you observe. So we said that immediate filtration in the field is super critical for these kind of validation tests. The big takeaways from this part of the study were that for our SOP for sample collection, we recommend that you clean the instrument, usually clean the instrument, put it back in the wherever it is in the mix liquor, for example, let it sit for a little bit, note your instrument reading, collect your sample right next to where the instrument or sensor is located, filter that sample immediately. And we also wanted to note that many different types of filters work. A lot of folks that we talk to, especially on the manufacturer side, recommend using a syringe filter with a 0.45 micron filter attached to it. But we found that even coffee filters work just fine. There's a whole range of different things that work. It's really just finding something that works for you and your utility. After that, make sure to put your samples on ice to keep them cool as you transport them back to the lab for analysis. For the analysis part, there are all kinds of good test kits out there that are available and reliable. I had some undergraduate students working with me, and they were able to use these Hawk TNT Plus test kits and got really good results with them. They're super user-friendly. So if you're at a utility that happens to have folks on a lab rotation or something like that could make a lot of sense. They are a bit more expensive. So if you have dedicated lab staff, they might not be the best choice for you. But there's a lot of different things that work for folks. The other part that we wanted to note was that for matrix adjustments, it's really important to only make those adjustments when they're needed and really pay attention to kind of the overall trends and not just have a knee-jerk reaction if you have one sample that seems to be off by a little bit. We talked to several utilities and manufacturers, and what they said was that trying to overcompensate for a seemingly erroneous reading will lead to sensor drift and will lead to worse readings down the road. And really, making sure that you have a good routine maintenance plan is going to be super critical for making sure that you can get good readings from your system. Keeping those instruments clean, keeping them in check, and making sure that your calibration is on track is going to be really important. A lot of these sensors come with an optional cleaning system that's automated, either an air blast or a wiper or something like that. And we found that those can be really helpful in making sure that your instruments stay clean and that you're getting the reading that you need. And so with that, I'm going to pass it back to Amy, who's going to talk about the decision flowcharts.
Fantastic. Thanks, Nick. All right, so it is my great pleasure to get back to our final destination on our canoe trip and talk you through two of the components that are there that are left. So these will be the decision flowcharts and the return on investment calculator, which you will see both of these are intended to be tools that help you as a utility or from whatever starting point to think about what makes sense in the next step. So jumping in on the decision flowchart, the idea is really to try to answer the question of whether it is worthwhile to invest in instrumentation for a biological nutrient removal process and for the associated control system that would be needed in a treatment facility. So we start with an initial screening, which just is some pretty high level considerations, move into a cost benefit analysis if the initial screening is passed. And then finally have some suggestions that we have pulled from our utility surveys and the other conversations we've had with folks in the industry that really are, in their opinion, determinations of success. So if we start with the initial screening, for us, it broke down to 4 things, really. Number one, are there nutrient limits? That is really important in determining whether it's worth the complexity and the cost in upgrading a facility and taking into account all of the information that you've been given so far. The second is the infrastructure that's already there appropriate for an upgrade, or would kind of the mapping of a new process not even make sense with existing infrastructure and you're thinking about a more major renovation? The third is there an ability for the utility to make a long-term commitment to actually upkeeping all of these sensors, to making sure that the data coming back are really useful for a control system, and that all of this investment will be worthwhile? And the last is somewhat related to the third, but on a human resource side as well as a financial side. Is there really buy-in from the whole organization for this kind of upgrade? Because it's not just the decision maker with the purse strings that's needed to make all of this work. As Nick said, there's a lot of legwork that you need just to keep everything running after the initial investment. So is the whole team that would be doing all of that work, soup to nuts, on board? So that's our initial screening. Kind of we need a yes, 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 yes to move forward. If it's not a complete yes, we have a few prompts for you to think about what we need to get there. So do we have a sense of quantitatively what we need to comply with our limits? Can we push a little bit and figure out what the savings are? Do we need to make a pitch for how we get there? Are there other costs that may be unique to this facility, or have we gone through the whole calculator that's been provided? And then finally, how do we bring everybody on board? So we're hoping that the tools that we're providing here are really a part of number 4 of convincing folks that there is a really good pathway to adoption, and try to simplify what might feel overwhelmingly complex at the beginning. Then we move on to the cost-benefit analysis. And here the question is really, can this make sense from a financial point of view as well for the facility? So what are all of the capital costs that would be needed? And here we're really thinking about all of the different things that might need to be invested in. So that could be a SCADA, it could be the sensors or the instrumentation. It could be if there's some part of the infrastructure that needs also to be changed alongside that. We need to think about what are the maintenance costs as we go through time. And this is really where our conversations with utility partners were incredibly helpful with giving a baseline and trying to put quantified information on this. As Maureen mentioned, this is not information that is typically easy to understand from a vendor website. So the best information we have is really going to examples of places where this has been implemented and asking them, what have you done? What did it cost? How complicated was it? And that's included in our ROI calculator. And then where are we benefiting, right? So actually, oftentimes when we approach these kinds of innovations, we're thinking that there's upfront cost and perceiving that as the most important hurdle that we need to face. But actually, implementation of a tightly controlled system and implementation of sensors that are bringing us back pretty continuous data streams has the opportunity for savings also. So we might have savings in energy consumption, we might have savings in purchase of chemicals, and we might actually have savings in preventing permit exceedances, right? So where is our potential for savings? And then the final is what performance do we think that we can really improve here? And so this is, partially tied to number 3, but really also about maybe more consistency, a performance that doesn't need people to be working at overtime hours, or what are the other potential benefits that can come out of this, rather not just like the numerical dollars. So the ROI calculator that we've provided, it's based in an Excel spreadsheet. It is relatively approachable. It gives a template for kind of working through that flow chart I just talked through. So it walks you through thinking about the capital costs on the, like I said, the SCADA control side, the instrumentation side, and anything else you might need. Thinking through what the O&M costs are, and there's a lot of good advice coming out of our utility case studies on that point. And then thinking about really what are all of the savings that we gain here. So it lets you get into a level of granularity to start a conversation within the utility about what are these trade-offs, these costs and benefits, and really numerically what is the potential benefit in terms of returns. The last one, I think we were really excited to put this here because this is often part of the conversation that gets lost while we're wrapped up in the complexity of the technology and the money. The utilities we spoke to who have implemented controls, sensor-driven controls, had a lot to say about critical factors of success that were not so much centered just on buy the right technology. So a lot of these were much more nuanced, such as, is the sensor actually in the right place in the within the system? And there were some really great talks that several of us saw this week right on this topic, where you kind of have to match what's happening in your own unique biological process with, for instance, the detection limit of a sensor. If you place it right at the end of a train where concentrations are really low, the gut reaction might be this sensor isn't useful in this application, but maybe just moving it upstream, you can actually get very usable data. That does take a little bit of trial and error, but can unlock real potential. The second is building trust within the organization about the quality of the data. So that's not just ensuring that we're actually getting usable readings, but also that there's a process for data validation. Examples that were provided by Nick in terms of making sure that the calibrations are up to date, only recalibrating when necessary, and making sure everyone using the data knows about these processes and can trust the data so they actually do get used. The third is the plant will change over time, definitely, and there will need to be modifications, and that will look different than it did before installation of a sensor-driven control system. So how is that going to happen? How is that going to happen in a technical way, but also in a human resource way, and in a validation kind of way? So similarly to the notes that Nick provided on sensor calibration, changing the control system is, again, something you don't want to do all of the time. You need to have a decision process for when is this really necessary and how do we make that decision? All right, and then this is my personal wheelhouse, is thinking about, this is going to generate a lot of data. So what is the plan there? Are all of these data being used only in real time by a control system and then we don't need them anymore? I hope nobody is thinking the answer there is yes. How do we save those data over time? How do we visualize the trends? How do we learn bigger picture things about what's happening in the plant from these data? This is actually an intellectual resource that most plants don't have if we don't have this kind of data logging that's happening continuously over time. So this can be an untapped resource if it's not taken advantage of, and is really a factor of success to make sure that there's someone on the team taking ownership of this and thinking about how we leverage the true value of the data moving forward. And then the last is really about organizational capacity. And this comes back to, right, the step one initial screening is making sure that the organizational buy-in is there and that there's a commitment to this moving forward for the long run. All right, and with that, I'm going to hand it over to Paul.
Wonderful, thank you, Amy. So we're gonna go, and we've gone down this journey down the river, looking at all of these different concepts of BNR, what's involved, and what decisions you might make relative to making a investment in putting in instrumentation and controls. Well, what we're going to do is now, instead of just, okay, we're going to do it and put it in the plant and try it out, we're going to have, you know, the ability to simulate this and try all of these different opportunities of how you would put in different versions of control. So with that, we're going to look at how do we simulate this? Simulate this using process modeling. And our project included a process model that included a whole bunch of different interactive layouts and options to simulate different levels of control. And they included interactive training exercises, and we'll get to some other additional options on that as well. But that included SRT control, whether you're using obviously the typical RAS and WAS concepts, DO control with managing and controlling airflow, ammonia-based aeration control with using DO as the intermediate parameter based on a ammonia-based setting, and in different locations in the trains, you could talk to some of the things or try some of the things that would be in there relative to, is it better to measure your DO, in the middle of the train or at the end of the train? Certainly different things like that can be investigated, and that may very much dictate or influence what type of sensor and control layout you would implement. Phosphate control using metal salt addition with a PID loop, and then nitrate control for denitrification with supplemental carbon addition and or controlling internal mixed liquor recycle pumping. Now the simulators can do a lot of different things, and we've set this up where you can do both steady state conditions, so relatively straightforward, plug in some things and get an answer, or run it under different dynamic influent flow functionality with normal diurnal changes through the course of a day, but also putting in the ability to put in wet weather events that would see, hey, what happens at my plant if my flow doubles because of a rain event, not additional loading, but just additional flow. So the simulator is comprised of, well, the software package is SimiWorks, which has been used in the industry for a number of years in a number of different ways, but it's based on a very robust process model, GPSX, that's been in the industry for decades, developed by Hydromantis over the years, but now Hatch. SimiWorks has been, in itself, has been available for over a decade and has been used for hundreds of different training events in WEF and in different regional organizations, and is a very big part of the WEFTech Operations Challenge for the last 9 years. So we're closing in on 10 years on using this for Operations Challenge. Now, this simulator uses a variety of different instrumentation, as one would expect if you've modeled before. You have almost an infinite number of things that you can put into the process model relative to instrumentation, that you know what's going on in different locations in the process. But we've made it simple so people can very readily apply different control features within that, both with a very open simulation mode that allows you to try a number of combinations of different approaches to control and operation, including combining many different ones, as well as previously prepared self-paced exercises that walks a user through step by step and allows them to see the changes and use those to allow you to demonstrate, well, what will happen if you move the ammonia sensor from point A to point B, or use different factors on your chemical addition that you're going to apply. Now, this is the appearance of the simulator. There's a upper level that has what looks like an isometric of a treatment plant, and you have all different sorts of data or things you can change within that. I'm not going to go into that because it's a lot better to see it real time. And I'm going to turn it over to Spencer Snolling, who is going to actually run you through a demonstration of some of the features of the simulator.
Thank you, Paul. So for the remainder of the demonstration today, I'm going to be showing you about SimiWorks. This is our simulator that we created specifically for WRF Project 5087. And in this particular simulator, it is designed to teach the BNR control concepts that have been discussed in the earlier part of the webinar today. We've created a simulator that allows people to experience and experiment with the different types of BNR control, specifically SRT control, chemical dosage control, and aeration control. And understand and experiment and do it in kind of an interactive fashion so that you can run this wastewater treatment plant under different control conditions and see how the different control schemes work and understand what the effect is both on the operating cost and also on the effluent quality. So I'm going to start out today by giving you a real quick tour of how SimuWorks works. And then we're going to run through a couple of the exercises so that you can see how DO control compares to ABAC control. And also we'll run through an exercise around ferric chloride dosing and using a controller and seeing how the different dosage points within the plant works. Okay, so as far as SimuWorks is concerned, you have this plant schematic up here at the top of the screen, and so I can interact with different parts of the plant by clicking on different buildings and the clarifiers and so on. And each time I do that, it brings up a different input menu that I can play around with here. So what happens is whenever I'm ready to go and I want to run a simulation, I can hit the start button down here, and it will update all of the outputs on the window here. On the right-hand side in the lower right corner here is the effluent quality. So this menu tells us what the effluent concentrations are, and we can see here that the TSS is less than 10 and the ammonia is less than 0.15 and so on. And the effluent phosphorus at the moment is showing 9.82 because we're not doing any sort of phosphorus removal here. We can start adding some chemicals to do that. So very simply, I can come here, click on this building, and if I wanted to change something, so in this case, I want to decrease the wasting, I can go here, type in a new value, and then I can rerun the simulation, and then immediately I'll get some results of what we call the steady state solution of the model. So this is as if the plant has now been running for a few weeks under these new conditions, and everything's kind of equilibrated and it's sort of settled into its new mixed liquor, for example. So those are ways that you can interact with the model. You can very easily and quickly move around. And the best part is that we have these training exercises. Now, these 5 exercises, you can go through one at a time, and you can, for those of you who are WRF subscribers and you want to download this, you can experiment at your leisure with all of these exercises. And as I mentioned, we're going to do a couple today, exercises 3 and 4. So I'm going to start with this ammonia-based aeration control. The way that you do these exercises is there'll be some text here in the lower left-hand corner, and you can follow along, read all the details about what it's supposed to do, and then it will instruct you about changes that you're supposed to make to the operation of this facility. So it'll take you through a number of explanations about what's going on and point at important things that you're supposed to deal with. So I'm not going to go through every single step today. I'm going to actually, because of limited time, do a very quick version of these layouts here. So what we want to do with this exercise number 3 is to compare regular DO control with ABAC control, ammonia-based aeration control, and show you how they are different with respect to the performance of the plant and also to the amount of energy that is required to do the aeration. So let's start out by using regular DO control. So I'm going to click on the aeration basin here, and we can see there's a DO controller. And we can see here that there are 5 set points. That is for the 5 passes, the 5 zones of this long plug flow tank aeration basin here. So that means this is going to be a fully aerated activated sludge tank. And if I run the simulation under those conditions, we can see here that the effluent ammonia is 0.06. That means, of course, it's doing completely full nitrification, and the DO controller is doing its job. So a couple of different ways we can look at what's going on in this tank is to open up this outputs menu here, and we can take a look, first of all, at the aeration tab. So this is showing us the dissolved oxygen concentrations on the top and the required airflows on the lower part of the menu here. And you can see that as desired, these 2.0 milligrams per liter of dissolved oxygen is being met. So across the board, this is 2 milligrams per liter. And we can see that different airflows are required for each zone in order to meet that requirement. So, of course, more air is required at the front where there's a heavier loading, and it decreases as the substrate and ammonia is being removed as it goes down the length of the tank. So we can also look at the nitrogen profile here as well. So we can see the ammonia is being removed almost down to nothing. There's a tiny little bit of nitrate. And of course, because we have full nitrification, we got lots of SRT, it's being fully converted to nitrate all the way through to the end of the tank. So that's for a steady state solution. I also want to look at a dynamic run. So a dynamic run is where there's going to be things that change over time. And so in this case, I'm going to run a 2-day simulation. And then we can see how the controller does its job, maintaining that DO set point. point. So you'll note here that these bars are moving up and down a little bit, and we can see on the aeration tab here, these air flows are adjusting to maintain the DO at the required set point. What it's responding to is actually a change in a daily diurnal pattern of the influent loading. So the diurnal flow is going up and down during the day. And we can see, if I look at this time series here, this is time on this axis, 2 full days. We can see here that, for example, the brown line is the DO set point and the blue line is the actual DO. So it's not a perfect controller. It's a realistic one that shows that it goes down a little bit above and a little bit below. But the airflow is being adjusted by the DO controller to maintain that flat DO set point. So that's zone 1, 2, 3, 4, 5. Here we can see, and progressively using less air in order to be able to match those set points. Okay, so one thing that we want to see then is, and I'm going to rerun that steady state simulation, is in this case we want to take a look at the amount of the amount of energy that's required to do DO control. So here we can see in this panel here, the energy and chemical cost is being shown. And in this case, it's showing $82,250 per year to be able to run this DO control at 2 milligrams per liter. So that's because we're aerating up to a full 2 milligrams. And so what we're going to do is now run it under ABAC control at steady state and see how that is going to work and how that's going to compare both in terms of the effluent quality and also the operating cost. Okay, now the way we do ABAC is that we turn on that ABAC controller, and then we have these two values here, tank 3 and tank 5. So what that means is we can actually take the ammonia signal that we're going to use in the ABAC control from the middle of the tank or the end of the tank. And I'm going to leave it on the middle of the tank right for now. This is there so that you can sort of experiment with and it's relevant to the choice of technology that you might be using for that ammonia signal, whether you're using probes or sensors or so on. Like some things are better suited to higher concentrations in the middle of the tank. And there's also an issue if you're trying to do control that, things might happen too slowly as well, depending on how that signal needs to be updated for the controller. So we're going to leave it here at tank number 3, and we're going to look at these ABAC set points. So what this does is this says we're going to take that ammonia signal, we're going to look up in this table what we want the DO set point to be. So for example, if it was half a milligram per liter of ammonia, then that means we'd be in the first row here and we would be using these relatively low concentrations of DO, half a milligram per liter across the board here. But if the ammonia was start to rise, like say we're having an increasing in loading to the plant and the DO and the ammonia went up to a higher value, 2 or 3 milligrams per liter, then we would move up this table and we would start increasing the DO set point. Now, just like the previous simulation, that DO set point, the DO controller will do the job of increasing the airflow. So in essence, this is two controllers working together. The ammonia controller trying to control the ammonia concentration by changing the DO set point, and then those DO set points are driving the DO controller, which is controlling the airflow. And so those two things working in conjunction will hopefully make for a very efficient system for doing nitrification. Okay, so I'm going to leave this closed, and then I'm going to open up those profiles again. Let's look at the nitrogen one, and now we have our ABAC controller on. I'm going to bring up that controller output so we can see, what those aeration systems are doing. So we're going to look at this DO control here, and I'm going to run. First of all, let's run a steady state solution. Before we get to the dynamics, let's run a steady state solution here so that we can take a look at these numbers. So in general, it's less than 0.1. So again, it's looking very similar like full nitrification. But note that now the energy required is now down to 69,000. From previously we had over 82,000. So we're seeing a significant decrease in the amount of energy, and that is partly because we're now aerating a little bit less. We're now using a little bit lower DO concentration in order to do that nitrification. And we also see a little bit like the effluent nitrate is a little higher than it was previously. So we're not quite as aggressively aerating under this control scheme. So now let's run that dynamic simulation, and I'm going to open that controller output back up again. So, and we can see here that our DO set points are different than previous. Instead of being at 2 across the board, they're now down at 0.5, and occasionally they bump up to 1 when there's a really high loading here. And so we can see that the set point is bumped up here, and then there's an immediate increase in the airflow as it goes all the way down to the bottom. And so therefore that is a more sort of sophisticated control, and it's keeping the DO low when it's okay to do that, when the ammonia is in a good place. But when those heavier loadings come, then it does bump up the set points accordingly. So let's take a look at how that ammonia in the effluent looks over time. If I click here and I see this is the 2 days simulation, we can see the ammonia is like pretty rock solidly low here at less than 0.1. And we can take a look at the nitrite as well. This is 0 to 1 milligrams per liter, so this is moving up and down, but it's still relatively low, less than 0.5 for the moment. Now, that's certainly higher than it was with the other controller, but it's still relatively low. And we can see that we've achieved some savings from doing that as well. Now, one question would be sort of how low can we go? Can we get even more savings, right? So what we're going to do now is we are going to drop some of these DO set points. I'm going to actually set this to go down to 0.3 milligrams per liter, and we'll just do that across the board here. And I'm going to drop these down from 1.0 to 0.5. And we'll do that across the board as well. And also we'll drop the 1.5 down to 1. And then that way we're now basically using the same concept, except now we're saying we're going to try and do it at a little bit lower aeration. So let's see where that gets us in terms of our steady state performance and our sort of average estimate of the energy requirements. And then we'll take a look and see what that looks like dynamically as well. Okay, so starting right off the bat here, we're seeing that we're still removing all the ammonia. It's like still around 0.1. Our nitrite is still definitely higher for sure. But we did knock it down another $4,000 or $5,000. So just to recall, we went from 82,000 down to 69,000, and now we're down to 65,000. But definitely we are now not overall achieving as good quality effluent. So if I run a 2-day simulation, let's do that again, and we can take a look at what's going on with the controller here one more time. And we can see that it's actually a little easier to see it on the ammonia tab here. We can see those DO set points are actually spending a longer time up at the higher value, right? Because it's not doing as much nitrification. So there's definitely a different behavior here. If I want to go back and look at these effluent numbers here, the ammonia, well, it's a little higher than it was before, but it's not varying very much, so it's still pretty stable. Nitrate, though, now definitely ranges across over 1 milligram per liter for sure. And so therefore, we're seeing that, we're getting only sort of bordering on partial nitrification. And so we've maybe pushed that a little bit too far. We've saved some money, but we're getting to the point where it's starting to impact the effluent quality. We can certainly see during those dynamic simulations the nitrite popping up here. Okay, so I'm going to reset everything now. We're going to go back to doing where we were before. We're going to do the ABAC still. So I'm going to run, I'm definitely going to run just a steady state simulation here. And then what I want to do though is take a look at how this is all affected by the SRT. So you may have noticed up here the SRT is being displayed. It was always around 10 days. That's probably because we have an SRT controller in place here. We can see this SRT controller right here. We can say the SRT controller is on and we have a set point of 10 days. So it was always wasting the correct amount of sludge in order to maintain that set point. So what we're going to do is take a look at what goes on, and I'll bring this other output up here again. We're going to see what goes on if we move to a lower SRT. So just to illustrate that all of these things are connected together, let's go to a 3-day SRT, and then we will run the simulation again. And in that case, we can see that there is an effect here. It's showing around a 3-day SRT. It's wasting a different amount. And we can see that there is some impact here. Our effluent ammonia is up to 0.15. That's a little higher than we had before. And in fact, if I run a 2-day dynamic simulation, we should certainly see some more dynamics happening around that. So we can see once the real push comes during the day when we're getting the higher diurnal patterns. Certainly, our ammonia is fluctuating a fair bit, and our nitrite is doing the same thing. So that means that we're seeing those effects of running at the lower SRT. Therefore, we may want to actually increase our DO settings in order to counteract that. The model is a really good tool to be able to investigate that relationship. And when I run at lower SRTs, can I still get really good improvement? Well, maybe if I bump up those DO set points, you can iterate and experiment all you want in this simulator to do that. I'm going to completely break the whole thing now, though, by going down to 2 days SRT, which is pretty tough to be able to do complete nitrification at that point. So, in fact, we can see here, the ammonia is now, going well above where it was before, up to 3 or 4 milligrams per liter. And we can also see that the nitrite is really high as well. So this is an interesting tool to be able to explore with all of those different aspects. Okay, so what I'm going to do is I'm going to move on now from talking about aeration. We're going to go to the other exercise that we had, and that is for doing ferric dosing control. So this is doing the dosing of ferric chloride to remove phosphorus. And immediately I'll point out the fact that we do have 2 different spots in the plant where we can do that. We have primary ferric dosing up here, which is ahead of the primary clarifier. So any phosphorus which is coagulated or flocculated and removed here with the solids. And then we have another secondary dosing point. And this is after the biological tanks. We're doing some dosing there, and then that goes into the secondary clarifiers where some of that will be wasted away as well. All right, so right now, I'm just going to run a real quick simulation where there is no dosage at all. So we can see here that this is pretty close to 10 milligrams per liter here of phosphorus. We're not really doing anything yet. So if I open up our controller outputs and I go to this phosphorus tab, where is it here? This one, we can see 0 dosage. And so our concentration at this point is now, up here around close to 10. And this one down here is also the same. It's a little bit lower at the second point because there's a little bit of uptake there as it goes through the biology. But those are not there's no real effective removal yet. Okay, so what we can do, I'm just going to move this over a little bit, is we can start by putting in some ferric dosing here. And we use a constant mass of flow here. We can put in 125 gallons per day in the initial primary ferric dosing. And we're going to run that 1-day simulation again. So you can see that the pattern, it goes up and down the effluent phosphorus. This is on the outlet side here before it goes into the primary clarifiers. That previously we were up here at around 10, and now we can see here it ranges between 3 and 6. And that is because we are, of course, dosing the ferric chloride, and it is reacting with the phosphorus, and it's being removed with the solids. Now, note that it goes up and down during the day. And the reason for that, of course, is that we are dosing a constant mass. But the amount of flow coming through this point in the plant does go up and down. So the actual concentration of ferric chloride actually changes during the day. So when there's more flow, there's actually less concentration. So therefore, it's not removing as much phosphorus. And of course, the increased flow means there's more phosphorus coming through as well. Okay, so that means we get partway done. We can see here the response at the secondary point. Even though we're not doing any dosing, it is now, of course, a much lower concentration as it passes through that same point. So what we can do then is we can actually change this so that it can have a controller applied to it. So I'm going to set this to 3 more days, and also I'm going to switch this over to a flow pace controller. And in that case, I'm going to set it for 5 milligrams per liter. So what's going to happen is we will continue on with the controller in place. So we can see now that controller is making changes dynamically to the amount of chemical being dosed in response to what's going on with the phosphorus. So it is now maintaining this 5 milligrams per liter phosphorus that comes out of this dosing point. And that's doing the job of removing phosphorus in a very dynamic way. So we have very stable phosphorus there. So 5 seems like a reasonable point. You don't want to lower it too much before you go into your bioreactors because you don't want to starve the bugs of phosphorus. So we can do that. We can do that there. Okay, so that's kind of a way of looking at the difference between just dosing a constant amount and dosing an amount that is there to achieve a phosphorus set point by allowing things to go up and down over the day. Okay, I'm going to actually set this back to constant flow, and I am going to just turn off the dosage there. And instead, we're going to put the same amount into the secondary dosage point. Right, okay, so now we've got 125 in the secondary point, and we're going to run a 2 or 3 day simulation. Actually, let's run a 1 day simulation. So we can see here now, of course, it's still at 9, almost 10 at the first point because we're not removing anything there. And then now down in that second point, that's after the bioreactor, but before the secondary clarifiers, now we're looking at getting a range of 3 to the 4 or 5. Actually, at the end of that simulation, it is actually 4.4. So that means that since we were only seeing about 5.5 before when we dosed the 125 at the front of the plant. Now that we're dosing it actually in the secondary dosing point, the same amount actually gets you a little bit lower effluent phosphorus at this point. And that is because, of course, some of the phosphorus is being taken up as a nutrient by the biomass itself and is being wasted out in the secondary clarifiers. So this is, again, a really excellent use of the simulator is to play around and take a look at how this relationship between the primary and secondary dosage points can allow you to sort of optimize your dosage because they have different effects and different sort of efficiencies for removing those things. Okay, so lastly, let's wind things up here by going and putting a controller on here as well. So I'm going to put this on and let's set it for, well, 1 milligram per liter down at the bottom here of phosphorus. So you can see that it is going to increase the actual dosage now. So it's now dosing higher and it's getting here a 1 milligram per liter across the board of soluble phosphorus. And if we look here, at our effluent, we can see it's 1 milligram per liter. The total phosphorus, of course, is higher because there's some of the phosphorus in the solids too, but we're kind of doing the job here. Okay, so I'll wind things up by saying that WRF subscribers can download a copy of this simulator and request a key code to activate it. And that is, as Sue mentioned, available for you for the year. And so you can experiment around, play with all of these things. And I recommend going through all 5 of these lessons to sort of have this interactive tool at your fingertips to explore and understand how all of these things work. Okay, thank you very much, and I'll pass it back over to you, Sue.
All right, great. Thanks so much, Spencer. All right, I'm going to spend just a few minutes wrapping things up, and we're really excited to get to some questions here. So we have thrown a lot at you today and want to make sure that you understand where you can learn more and how you can access all of this information. So this app, as well as information on the simulator, can be accessed from the WRF website if you search for Project 5087. The great thing is that this is a public plus project, so you don't have to be a WRF subscriber to be able to access the app. So you'll be able to get all of the information that we've been walking through on the tools. Our project report is included in the tools. So if you'd like to go and read a summary of all of the tools and the work that we did, there is a report. It's downloadable as a PDF from that app as well. The Adventure Hunt, just a little background information. It's hosted from Woodard and Kern, so we're calling it an app. It's a web page. The path is here, but you can also link to it right from the WRF website. The simulator is hosted by Hatch, and that is going to be available to WRF subscribers only. And that you can reach out directly to Spencer, and we'll have our contact information up at the end of this presentation. But you can just send him an email, and he can get you hooked up. it's going to be available for WRF subscribers to play with for a year. So through, I think, September 2025 this year. We also do use this app in training forums, and there are absolutely going to be more opportunities to play with the simulator. Paul Dombrowski is going to be leading a couple of trainings coming up. One is going to be on April 29th at the Upper Blackstone Clean Water Plant in Massachusetts as part of the NWEA WEFMAX that's happening there, and also looking at a tentative training in Minneapolis in July. So be on the lookout through your local WEAs for some additional training opportunities with the simulator, but also feel free to reach directly out to any of the co-PIs, and we can talk to you more about what those opportunities could be. Okay, just kind of want to recap and pull all this together. And you know, when we worked through this and developed these tools, it was really in the spirit of providing these benefits to folks who are going to access the information. We really want folks to gain a baseline understanding of in situ sensors and wet chemistry analyzer technology. What that could be, that's just a small part, though, that we learn for controls and experiences. So we also have case studies embedded, and hope that by sharing out what others have learned, that will, again, help accelerate the knowledge learning within our whole industry. We want to be able to help you streamline your decision-making process and really focus on evaluation of the most applicable systems, as well as providing a rubric to help think through those steps. And then finally, this simulator has been a really fun tool that folks who have used it, you know, started calling it a video game. And it really just is a really great way to try out and reinforce a lot of these controls concepts that we presented today. So this is the last slide. Just want to kind of wrap up with some of the big picture takeaways that we brought out of this project. And one is that, you know, the sensors and the analyzers aren't the only reason around whether or not to adopt an instrument-based control system, and aren't the only reason why it's slow. There are a lot of other factors, and it really points often to the human side of things, and the consideration of the full life cycle. So just beyond the capital investment and the accuracy of the sensors, but thinking about O&M, implementation, management of the data. So we've identified these critical success factors, and this is based on all of the feedback that we received through the utility surveys, through the case studies, and our own experiences working with these types of systems. And it's really making sure that you're matching your instrument to the location, planning for ongoing O&M, making sure that you've got plans for cleaning and validation testing, and adjustments to your control system that will need to be made either seasonally or as your influent characteristics change. Design a validation sampling plan so that you build trust in the instruments. That's often one of the reasons that folks walk away, is they don't inherently trust what the data are telling them, and don't especially trust them for controls. So being able to build that trust in the instruments has led many folks to success. Developing a strategy for data management, matching the system complexity with the need, and understanding the costs and benefits. You know, if you've got a 3030 BOD TSS plant, then you know, an advanced nutrient control system like ammonia-based aeration control is too complex and not applicable. So really thinking through what your performance objectives are, and then thinking about the most appropriate controls and instrumentation for that. And then finally, can't again reinforce enough how much knowledge the other water resource recovery facilities and all of the representatives who were involved in this study had the case study contacts all were really willing to share their information. They've participated in some of the panel discussions that we've had and have a lot of really, really great information. So don't hesitate to follow up directly with them. But again, just want to thank you all for your time this afternoon, and thanks to all of our partners again for the support for this project. So with that, I think we're ready to go to Q&A.
All right. Yes, that thank you. I would like to thank all our speakers for presenting all these presentations in such a smooth and very exciting way. So we have received quite a few questions. So if we don't have time to get to your question, don't worry. We will be emailing whoever asked questions after the webcast. So let's get started with some questions. I think the first question is, what is the difference between analyzers and sensors? Amy, do you want to take this question?
Sure, I can take that question. This is maybe a little bit loaded, so I will qualify with saying how we defined this, and I know there are some different definitions used across the field. We essentially thought about sensors as a device which gives us a number in pretty much real time with no chemical alteration needed to the sample, whereas analyzers are something where there's perhaps wet chemistry or some other alteration to the sample that's happening before a measurement is being made. And those numbers could still be coming potentially in real time, but they might be delayed. So for instance, a total phosphorus analyzer typically takes almost an hour to do that measurement because there's a heating step that's required in order to get that measurement.
Great, thank you. So the next question is, I believe for Paul, are there any pure oxygen plants in the case studies?
Yes, the city of Holyoke, Massachusetts is a HPO plant that's in the case study. It's a little bit unique in that they've opened the tank up to atmosphere, so it's not a closed vessel HPO, but they are using pure oxygen and mixing the tank, using that or aerating the tank to use that, and they do have an anoxic zone in the initial step of the train where they get seasonal denitrification.
Great, thanks. So Nick, what is in the solids that change nitrate?
Yeah, that's a good question. So a lot of these sensors are deployed in mixed liquor conditions. And so it's a lot of the biological activity that's really pushing the change in the nitrate concentrations if you don't do that filtration.
Great. I think the next question is for Sue. Are there preferred locations for sensors or analyzers, including like a depth in the tank?
Yeah, that's a great question, and something we talked a lot about with our case study participants. And one of the biggest points was make sure you put it in a location where it is accessible for O&M. If it is really hard to reach and you can't do those regular cleanings, then it makes it really hard to validate that data and trust the results of it. So, I think that's number one most important thing. The second is to work with the manufacturer. They've got recommendations as far as locations of depth of tank, but also really matching the concentration range that you're expecting to see with what the sensor can do. So Amy, when she was talked a little bit about when you're using an ammonia sensor, like an ISE sensor, making sure that you've got that placed in a portion of the tank where it's actually able to read ammonia, so it can stay in calibration. We've seen a lot of examples of folks putting those ammonia sensors at the end of the aeration tank and having a lot of trouble with their ammonia-based control system. So folks are moving it up in the process where they're able to see more consistent reading. And then when you're thinking about things like analyzers, if you're pulling from like a a stream out through a wet chemistry analyzer, making sure that you've got all the accessories that are needed, heat tracing, filtration, for example, just making sure you're thinking through how that sensor or analyzer is going to make it through all of the seasons. And then the last thing is putting it in a location, again, where you've got some flow across it. Oftentimes, if you put it in a dead zone, you'll see more rapid fouling of that sensor. So it is site specific as to what works for some plants and what works for what doesn't work for others. But those are kind of some of the major themes that we picked up on. Again, just coming back, that the most critical one is making sure you're putting it in a place where you can access it.
Thanks. Maureen, here's a question for you. So what kind of challenges have you seen with DO control and sensors?
Yeah, so I mean, I think in terms of the sensor itself, the DO sensor itself, with the optical sensors that are most predominantly used, I think people are having pretty good success with the accuracy of those readings as long as they're keeping them cleaned. With it being one of the ones that's used most, we got a lot of feedback on the frequency of the cleaning, and most people really are doing it weekly to maintain those readings in an accurate range. But in terms of the overall DO control, like your aeration control scheme, the DO is often just a portion of that. So I think where people, especially if they're trying to implement it at an existing facility, where they can run into issues are actually limitations on other pieces of equipment. So, if you're trying to operate and control to a lower DO, can your existing blowers actually do that? Or do you need to make modifications so that you can get more turn down? Are your valves, if you need to be using them as flow control valves, are those sized appropriately? Are you going to be throttling back on them too much? So I think when you go to implement it at an existing facility, you have to look at kind of all of the pieces that go along with the aeration control scheme. Across any of them, you need to have, strategies for how you're going to drop out poor readings. Are you going to maintain or the last reading, or go to a set point just so if there are issues with a DO or an airflow meter or something like that, like how that's being managed by your control scheme. And honestly, I think in my experience, the tuning that happens with the aeration control scheme that's implemented, the overall scheme is critical to getting good performance out of it. So those are some of the things that come to mind for me.
Great, thank you. So back to you, Sue. I think the question is, the study is geared toward, the levels of nitrogen and phosphorus in municipal facilities. So what kind of challenges do you feel an industrial treatment system will have with the use of in-situ sensors where, ammonia and nitrogen concentrations can be between 800 to 1,000 ppm?
Yeah, that's a great question. And I definitely will say that the feedback that we got as part of this study really was focused on municipalities. I think some of the core tenets and themes that we were seeing around consideration of O&M, cleaning procedures, setting up good data validation would definitely apply. I think it's really, again, also matching the sensor to the environment. So making sure that if you've got really high ammonia concentrations, that you've got a sensor that is able to manage that system.
Great, thank you. So, the questions comes in during the presentation. Spencer, we have seen quite a few questions on the simulator. And we have only like 6 minutes to go. So let's pick some simulator-related questions for you, Spencer. So okay. Can the simulator be set up to run as an SBR?
Yes, not this particular simulator, but it is possible to model SBRs and do exactly the same thing. Now, this particular simulator for this project is not an SBR. It is a regular conventional activated sludge. So the answer is no, you can't do an SBR with this one, but possibly if we continue to develop this, we could put in an SBR version of it as well.
So what was the highest flow used in the simulation?
That's a good question. I believe it got up to around 3 or 4 MGD. It's a relatively small facility, I think, at this point. But yeah, it was something in the neighborhood of 3 or 4 MGD.
Cool. So does the simulator only run a conventional activated sludge process, or can you run any other types of processes like high purity oxygen?
Right. So similar to the question about the SBR, this particular plant is conventional activated sludge. However, our underlying simulator, that's actually the engine that drives all of this, does have models for SBR and MBR and HPO and a number of other unit processes.
I think there are some questions. I think Sue answered those, but let's make it clear. So can the simulator be used free of charge? And is the simulator available on the WRF website? Can you guys repeat, kind of expand again?
So the answer is yes, it's being made available free of charge to WRF subscribers. And the way it's not hosted on the WRF's website, it's actually hosted on our website, Hatch. So what we would like you to do is to email me. My address is up on the slide right now, spencer.snowling@hatch.com. And then I'll point you to the right place to download, and you'll request a key code, and then we can activate that for you.
Great, thank you. I just see a question coming in from Nick. Have you noticed a big difference between filtering samples immediately versus filtering once the operators get to the lab? For this facility, samples are taken daily and not iced.
Yeah, that's a good question. We actually found that the concentration can change enough to make a difference, even within 10 minutes, depending on conditions like temperature and some other things like that. So our recommendation is really to filter immediately, and there's lots of different ways to do that. Even using something like a standard coffee filter, if cost is an issue or something like that. Coffee filters work great for this. You don't need to necessarily have that kind of like 0.45 micron filter to be able to get what you need to out of this and still have good, reliable results.
Thanks, Nick. Back to you, Spencer. So would this simulator ever be used for upset conditions or for troubleshooting? For instance, P-in flock, poor settling, or filamentous bacterial outbreak?
So the answer to that is yes, you can certainly use the simulator. In fact, that's one of the most common uses of a simulator, is to be able to investigate process questions and find out sort of what's going on and what can I do to operationally to try and sort those questions out. Some of the settling things, our settling models are there. They do sort of accurate mass balance and calculations of overflow concentrations. The biological part is really the main focus of them, and that's sort of the part that does the best predictive element of it. There are filamentous bacteria types of models out there, although that's not part of the simulator that I'm showing you today. But yes, certainly. Paul mentioned that that this simulator is used in the Operations Challenge competition. Is in fact exactly doing that thing. We give them a plant that's not set up so that it starts in a place where it is not performing well, and what we do is instead we ask them to make changes to overcome whatever the problem is, to diagnose, troubleshoot what it is, make changes, get it into the right place, and meet their targets. And that's how they score points for the competition.
All right. Thank you. I think that's exactly the time for us to close. It's 2:30 in Mountain Time now. So I would really want to thank the team for the excellent presentation and the audience for the great questions. As I mentioned, for any unanswered questions, we will email you the answers after this webcast. Thank you so much.
Thank you.